I've replaced all the electrolytic capacitors, and I now have just a little bit of sympathy for the repairer who'd previously caused a lot of damage over in this area. I already knew that the +2 circuit board is rather more prone to being damaged than those from earlier versions of the Spectrum, and in fact rather prone to damage compared to many circuit boards I've worked on. However, this one seems to be particularly poor in that regard, and unfortunately I caused a little bit of damage while doing this replacement. In one case, a pad and a couple of its connected tracks lifted off the instant I touched the joint with my soldering iron, so I've had to fit another metal eyelet to repair that damage. This of course led me to ask whether it was really necessary to replace all those capacitors. It's not so critical in the +2 compared to the earlier 48K Spectrums, where failure of some of those capacitors can destroy the lower RAM. However, here the original ones were quite old and won't last forever. It isn't possible to fully test them without disconnecting them from the circuit, and I certainly don't want the Spectrum to fail due to a simple capacitor going bad, say a year or two after this repair, so I think on balance I still did the right thing in replacing them. After doing that, I had the Spectrum running for quite a while, seemed to be working reasonably well, and then all of a sudden, while I wasn't even touching it or any of its connections, the picture on the television went blank, and the current limit on the bench power supply, which I'd set to just over 1 amp, activated. It didn't take me too long to track down the cause of the problem, and it was this, the Z80 CPU. This one now seems to be completely dead, and it has a partial short circuit between its power supply connections. Fortunately, the Z80 is still made, so I fitted a new one. I'm also still occasionally encountering problems with an intermittent connection to the voltage regulator here, so maybe it'd be best to replace this connector. Everything was going well, but then I noticed after this Spectrum had been on for quite a while, maybe 20 minutes or more, that resistor R79 was becoming quite warm again. This is the one that originally got very hot, hot enough to burn my finger. It doesn't do that now, but it's still getting quite a lot warmer than I think it should. So I've been making some comparisons with another +2 that I think's in perfect working order. Straight away I noticed that it drew about 100 milliamps less from the external power supply, and that was compared to this Spectrum with its original CPU in. I've now installed the new CMOS CPU, and that uses less power anyway. But ignoring that change, there's still something in this +2 that's drawing more current than in my other good one. And R79 in that +2 barely gets warm at all, so it suggests that something's still not quite right. I then noticed that this IC over here, IC3, which is the controller for the serial and keypad interfaces, is becoming quite warm as well, and it doesn't do that in the other +2. So that suggests this is probably the cause of the excess current consumption. And in fact, I pulled that IC out of this Spectrum, and the current consumption fell by about 100 milliamps, and R79 stopped getting hot. So that's fairly conclusive. But why would it be doing that? It's possible IC3 is faulty. I haven't yet carried out any tests to see whether or not the serial interface, for example, is working. But this IC is the only thing in the Spectrum that uses the -12 volt output of the voltage converter circuit, and that's not something I've looked at before, so I decided to measure it. I switched the Spectrum on, and over here is the 12 volt output, which I've measured before, and indeed it's sitting at 12 volts, and just next to it is the -12 volt output. It's giving -13.8 volts, and in fact I've seen that reach -14 volts once the Spectrum's been on for a while. Now I think that's a little bit too low. In other words, the difference between it and the 0 volt rail is too high, and maybe that's causing IC3 to draw too much current. I want to try an experiment to see whether I can do something, see whether that is the cause, and see whether I can do something about that. Here's the circuit diagram of the voltage converter again. Now the 12 volt output here is actively regulated, And as I mentioned before, that's because a portion of it is fed back via this resistor. In fact, there's a divider formed by this resistor and this resistor here, and the regulated 5-volt supply is used as a reference. But the minus 12 volt should just roughly mirror the plus 12 volt output. So what I'm going to try doing is inserting some additional resistance in parallel with this resistor here, so that will lower the overall resistance, and that should reduce the voltage of the 12 volt output and then increase the minus 12 volt output. Terminology can get a bit confusing. By increase I mean make it closer to 0 volts, so the difference between here and here will be less. So I'll switch the spectrum off again and use these leads to attach the additional resistor. It's not always a good idea to use long flying leads like this for attaching components to a circuit, but I don't think it'll cause a problem in this case. This is R55 down here, so I will clip these leads on. I'm attaching a 10 kilo ohm resistor in parallel with that, which will make the overall resistance of R55 about 1.5 kilo ohms. Put that carefully to one side, and let's switch on again. I've got the output connected up to a television, which I don't think I need to show you, but I've got a good clear picture on there, so the spectrum's still working. Let's have a look at the 12 volt output of the voltage converter circuit now. 10.67 volts, so that's certainly decreased by quite a bit, but clearly it's still enough for the TEA2000 composite video generator to operate, because I still got a good colour picture on the display. And over here is the minus 12 volt output, minus 12.5 volts. That's not so bad, and I found this to be minus 12.4 volts in my other plus 2, and that was without this additional resistor added. So I'm going to leave it on for a while now and see whether R79 and IC3 start to heat up again. The spectrum's been running for about 15 minutes, and R79 is not warm at all, and IC3 is only a bit warm, not as hot as it was getting before, and the total current draw by this computer is now about 50 milliamps less than it was before I added that additional resistor in parallel with R55. I've been looking more closely at how the serial and keypad ports work and carrying out a few further tests, and I've come to the conclusion that IC3 is faulty. Its datasheet says its maximum permitted power supply voltages are plus and minus 15 volts, so the supplies being provided by this spectrum shouldn't cause it a problem, and I don't think I'm going to need to do anything to adjust the voltage on the minus 12 volt supply rail. But let's have a quick look at what I might try if I wanted to do that. Here's the diagram of the voltage converter circuit again, and as I think already described, the oscillation of this part of the circuit generates an AC waveform here, and that's rectified by these diodes to generate the 12 volt supply, and that's regulated via this feedback loop. This same AC waveform is then coupled through capacitor C25 and rectified by these diodes to provide the minus 12 volt supply. Now if I wanted to increase the voltage here, I might experiment with slightly decreasing the value of capacitor C25. For some reason the circuit designer chose to use 47 microfarads here and 22 microfarads here. I don't know whether that's important. I might try making some calculations to see what the reactance of these capacitors would be at the types of frequencies this circuit oscillates at, and I suspect that by reducing this by an appropriate amount I could increase the voltage here. Another thing I might try would be introducing a little bit of series resistance with capacitor C25. Probably not very much needed. I could do that just by experimentation or calculation after measuring the current drawn on this supply rail. Now the internal series resistance of capacitor C25 will probably increase slightly as it ages anyway, so with this being a brand new capacitor, the voltage here is probably at the lowest point it will ever be. Anyway, I don't think I'm going to need to make any alterations there. As I said, the power supply voltages are within the range that are permitted for IC3. Here's another section of circuit diagram. The connectors for the serial and keypad ports are shown on the right hand side. IC3 here is a line driver IC that connects to the output lines of these two ports. And there's a separate receiver IC, IC5, that's connected to the input lines of the ports. The actual control of the ports is done by the AY sound generator IC, this one here IC4. In addition to its sound generation capabilities, it has an 8-bit general purpose I/O port. These are these 8 connections here, and they can be configured to be input lines or output lines, but all must be one or the other at any particular moment, and they can be controlled by software. The Spectrum's powered on and running this program. What it does is to configure the AY sound controller's I/O ports for output, and then it simply loops, switching these 4 lines here between high and low. These all connect to the line driver, and that should cause the corresponding outputs of this driver to switch between their high and low states. By the way, while I was writing this program, I discovered that there's an error in the +2 manual and in the later +3 manual, where it says that bit 6 of the AY chip's register number 7 should be set high to configure the I/O port for input and low for output, whereas in fact the reverse is true. So it's always worth checking the datasheet to make sure. So now that program's running, I can use an oscilloscope to have a look at what's going on pins 11 to 14 of the AY chip to make sure that's working properly, and then I can have a look at these pins 3, 6, 11 and 8 of the line driver to see what they're doing. So this is pin 11 of the AY IC. Again, that's switching between 0 and 5 volts. There's pin 12, 13 and 14. So it looks as if the AY's outputs are working properly. Now let's move over to IC3 and have a look at the first of its outputs, which is on pin 3, this one here. And there's nothing happening there. It's sitting at around about 0 volts, which I don't think is right generally, because if its input is low or high, it should be at around about plus or minus 12 volts. I don't think it should ever be at about 0 volts. Let's have a look at its next output, which is on pin 6. It's doing exactly the same. Pin 8. Nothing's happening there either. And pin 11, which is its final output, the same thing there. So I'll switch the power off. And I haven't got a new one of these ICs, but they are still manufactured, so I can get one. But I've borrowed one from another +2, so let's try changing IC3. Here's the replacement. Now I'll load that program again. The program's running again. I also note that the computer's current consumption is around about 40 to 50 milliamps less than it was with the faulty IC3 installed. So let's go straight to the output pins of IC3 now with this hopefully working one installed. This is pin 3. Excellent, it's switching between approximately plus or minus 12 volts as it should do. Now pin 6. pin 8, and finally pin 11. That's good news. So it looks as if at least all the output lines of the serial and keypad ports are now working. Having confirmed the serial and keypad port outputs work properly, I also want to check the inputs, since it's possible that whatever damaged IC3 has also affected IC5. So I'm going to run this program. It configures the AYIC's I/O ports for input, then reads the value of that input as a single decimal byte, displays that value, and then waits for it to change before displaying the new value, and so on. While that's running, I can then use this jumper wire to in turn connect each of the inputs of IC5 here to plus or minus 12 volts, which I'll obtain up here at pins 1 and 14 of IC3. So the program's running, and the first input on IC5 is pin 1. I need to be very careful here and make sure I don't connect a power supply voltage to anything other than one of the inputs. So I connect that to plus 12 volts. That's not having any effect, so perhaps that corresponds to that input to the AY chip being high. Let's try minus 12 volts. There we go, that's triggered a different value, so I think that input's working. I'll try the next one, which is on pin 4. So we know we should have an effect when I connect that to minus 12 volts, so I'll do that there. Yes, that input seems to be working. The next input is on pin 10. Pin 10 here, connect that to minus 12 volts. Yes, that's working. And finally, the fourth input is on pin 13. Excellent. It appears the input lines are working too, so I can move on and assume that the keypad and serial ports are working perfectly. By the way, so far as I know, the keypad port on the grey case plus 2 is exactly the same as the auxiliary port on the later plus 2 and the plus 3. I think it was simply renamed. With the serial and keypad ports now working, though I notice that IC3 still gets rather warmer in this spectrum than it does in the plus 2 that I took it from. But I can't find anything wrong, so I'd leave that for now but just keep a close eye on it during my final testing. I've just made another modification, and that's one you may have seen before if you've watched a previous plus 2 repair video. That's repair video number 4, and I recommend you have a look at that if you want to know more about this change. Basically, I fitted a Series LC filter composed of an 82 picofarad capacitor and a 15 microhenry inductor between pins 8 and 17 of IC2, the TEA 2000 composite video generator. You can see these components here. This filter helps remove any unwanted interference from the luminance signal that would otherwise be wrongly interpreted by the display as part of the chroma signal. Fitting this filter drastically reduces the cyan and yellow ghosting effect that appears on characters on the display. In this case, it doesn't seem to have reduced it quite as much as usual, but it's made a big improvement. I've also slightly adjusted the core of this inductor up here, which tends to have a small effect on that ghosting, but didn't do much in this case. I've also just removed this capacitor, C31, which was fitted on the rear of the circuit board. It connects the frequency modulated 6 MHz audio carrier that's generated by IC11 to the TEA 2000, so it'll be present on the modulated RF output. but that also means it's added to the composite video output at the DIN connector. That's not necessary and sometimes causes a problem. However, I'd still like the audio carrier to be present on the RF output. Normally, I do this by reconnecting this capacitor, or a new one, between IC11 and transistor TR2's emitter. Now I've just noticed that this circuit board, compared to some other plus 2s, in fact has a pair of pads down here marked C31. And on investigating further, I found that if I were to install the capacitor here, it would link the carrier to TR2's collector. Now given the topology of the circuit here, that should work too. So I'm going to install this capacitor in that position and see whether that works. I've also checked the orientation of transistors TR4, TR5 and TR7. These are often installed the wrong way around, and I found that to be the case in this spectrum, so I've refitted them correctly. One of them, TR4, buffers the composite video signal before it's fed to the DIN connector. Again, see repair video number 4 for a closer look at this possible problem. I've refitted capacitor C31 into the place marked for it on the circuit board. And now while I can get a good picture on the television using the RF output, there's still no sound. So I've started the spectrometer test mode, which can be done by pressing down the brake key while turning it on. That causes a picture of coloured vertical bars and an intermittent audio tone. And I've connected the output of the RF modulator to this spectrum analyzer. I found the main video carrier at 591.8 MHz, represented by the largest peak in the centre. That's about right for television channel 36. I think it should be 591.25, and I might try adjusting that later. There's a control on the modulator for doing that, but that doesn't matter for now. However, the frequency modulated audio carrier should be exactly 6 MHz above that. The scale here is 2 MHz per division, so that would put 6 MHz on this line here. And I suspect that this peak here, just to the left of that, is the audio carrier. It's at a slightly lower frequency than it should be. But first I want to confirm that really is the audio carrier, and I can do that first by adjusting the controls to centre that peak. Like that. And now if I bring the scan width down to 0, the receiver in the spectrum analyzer will demodulate that, and we should be able to hear the tone if it is indeed the audio carrier. I probably didn't do a very good job at centering it, but yes, I can certainly hear the tone. Perhaps if I adjust the center frequency slightly, I might be able to improve that. There's still a lot of noise, but we can clearly hear the tone. So yes, that definitely is the audio carrier. I've brought the horizontal scale back to 2 MHz per division. So that is the audio carrier, but we can see it's not at the right frequency. That's probably why the television can't pick it up. So what I'm going to do is adjust the horizontal scale now to 1 MHz per division. And try to bring the video carrier back on display. There it is on the left. And I'll centre that as best I can on that vertical line there, which means I now want the peak of the audio carrier to be 6 MHz to the right of that, on this line here. Now the carrier frequency can be adjusted by rotating the core of inductor L5, which is right next to the audio carrier generator. So I'll try adjusting that now and see whether I can bring it up to 6 megahertz. It's increasing now. There we go, that looks about right. So I think the next step will be to connect the television again and see whether it can receive audio. And if not, I'll probably use a frequency counter to examine the output of the audio carrier generator, and then I can adjust it more precisely to be exactly 6 megahertz. As soon as I reconnected the television, this is what I heard. I've since made a very fine adjustment to L5 just to make the sound as crisp as possible. I'll also demonstrate how the display looks if I use the composite output. So I switch the television to use that, and I'll just use a flying lead to make a temporary connection, so there will be a bit of interference, but let's see how it looks. I'll press the reset button. So that's how the initial menu looks, and there's hardly any sign of the cyan and yellow ghosting, so the filter that I added to cut that out is certainly doing a decent job. I've also checked the composite output with an oscilloscope and was able to confirm that the audio carrier is no longer present there.